Hi everyone, so now we're going to move on to the next section in Steck 7.7 on finite gain analysis. I think I do the next section also, 5.8, but we'll see. Let's see how long this lasts. Okay, the finite gain analysis is a way for us to quantify how in real life, right, the op-amp does not have infinite gain. It has a large gain, right? If you just put the two differential input into it, it has a large gain. Remember, this gain is called A. It's also known as the open loop gain. Unfortunately, I split that into two different lines. Makes it hard to circle. Okay, and this gain is not infinite and not instantaneous. Okay, so in the real physical op-amp, we want to just kind of quantify how big of a problem this is, and why does it having this negative feedback loop, meaning you're basically taking the output and putting it back in the input on the negative end, mitigate this sort of situation. Okay, so let's go back to the non-inverting amplifier again. I'm going to keep doing these examples. Okay, you have the Vn at the non-inverting input, right, and then you have a voltage divider at the output, and then in the middle of the output, you put that back in the fit that back into the inverting input. Okay, and you can use the golden rule. You're going to derive, you have hopefully in your previous homework, that the gain is going to be 1 plus R2 over R1. Okay, but in reality, right, this is actually the actual gain is this open loop gain that we talk about, and the difference between Vn plus, meaning the non-inverting input, and the inverting input, right? Because this is just a differential amplifier. That's all this thing is. Okay, because that's actually what the op-amp is doing, right? It's taking the difference between your inputs and amplifying it by, 0.5000 or whichever op-amp we're using. Okay, so let's derive what happens when we don't assume this to be just so large it doesn't matter, right? Let's just have it as a number that we're going to quantify how the op-amp behaves if this number was finite and what its dependence is. Okay, well, Vn plus, right, it's just Vn, right, it's directly connected, but Vn minus is actually proportional to Vout. So we have Vout on both sides of this equation. Okay, well, if we wanted to calculate gain, we need to move all the Vouts to one side. Okay, we're going to use this ratio of R1 over R1 plus R2, which is the voltage divider equation, right? I'm going to use that so much, we're going to, do a substitution in there, and just call it eta. Okay, all right, so doing that substitution, basically this just becomes eta, right? And if we put that back into equation 7.39, right, then Vout is actually whatever the open loop gain is times Vn minus eta times Vout, right? Because we just did an exact substitution for Vn minus. Okay, solving this for Vout, so it's just a couple of steps of algebra. You're going to find that, well, the actual gain is, right, is A over 1 plus eta times A. Okay, so that's kind of nice, right? If we make eta, right, well, eta times A much bigger than 1, meaning we're taking kind of the limit as A goes to infinity, right, with this high gain approximation that we keep using when we're doing our op-amp analysis. What happened is that the gain, right, this in this limit, right, the A's actually disappears, and then what happened is that the gain actually is just inverse of what eta is. And then if you invert eta here, right, invert this, you're going to get 1 plus R2 over R1, which is exactly what you expect, right, for the non-inverting amplifier. We're going to call this G infinity. Okay, G infinity means if we assume that the open loop gain is so large or approaching infinity, right, that's the gain of the amplifier in that case. Okay, Okay, we're going to see how the real gain will compare to this. Okay, all right. So if we take a to be large, but some finite number, so we don't take it all the way out to infinity, right? We go back to this equation here where it's just a over 1 plus eta times a. And the book does this in one single line. So I'm going to break it up into a couple of lines to derive this for you. Okay. So first of all, what I'm going to do, let's see, go up here, up, just so go in the right direction. Okay. Right. What we want to get to, what I'm going to do is multiply the top and the bottom by, let's say, not n, eta times a to the minus 1. I'm going to do the same thing on the bottom, so I'm just multiplying by 1, so that's perfectly safe, right? One factor of the a cancel out with this one because this one is in the denominator because of negative 1 power. The numerator is left with eta to the negative 1. These exactly cancel, but then this multiplies n. Sorry, the n a negative 1 multiplies to the 1, so we keep that. Kind of just inverting a lot of stuff. Okay. Now what we can do is that, well, since we know what g infinity is, which is inverse of eta, right? The numerator is actually g infinity, okay, divided by g infinity over a, because this is actually a fraction, right, plus 1. I'm sure I did that algebra correctly. Yeah. Okay. Okay. Then, right, this is I'm going to factor this g infinity out. Okay. When you factor this g infinity out, let's see what you get. Well, you get 1 over g infinity over a plus 1. Okay. And I wrote this down somewhere. This is just a expansion find that expansion for you guys over here. Oops. So this should be a binomial expansion. So I'm going to write down the general form here. 1 over a plus b is approximately 1 over b, 1 minus a over b. I'm just going to double check that real quick. Let's make sure. Let's see. Yeah. So a over b. Yeah. I mean, this technically goes on. So this will be the sign switches. This will be a squared over b squared. Then the switch signs again. A to the third, b to the third, and so on like that. Okay, but we're just going to keep these first to the first order. Let's see. Go back to the recording. Okay, so in this case, basically our a is g infinity over capital A. Our b is nice because it's just 1. So this g is approximately, the g infinity stays. And then you have this fraction is approximately 1 over b. Well, b is just 1. And then 1 minus a over b. So a is g infinity over a. Over that. Am I doing that right? That doesn't look right. Let's see. Okay, so yeah, so that's right, actually. Okay, so what we're going to do is we're going to define something new. We're going to define that negative g infinity over a as equal to the delta g. I'll tell you what this means. Okay, Let's double check what the book does quick. Analysis. Yeah, it's doing this in all one line plus a definition. Okay. Right, yeah, so it's defining negative g to the infinity over a as delta g over infinity. Okay, this may not make much sense because, well, you have this cross multiplication here. But what it's actually trying to do is defining a fractional difference, right, in the gain, right? Because this delta g is some difference in the gain, and then g infinity is the idealized gain. Hopefully that makes sense. So that's what this number is, okay? So what we can do is then we can replace this with the gain is approximately still the gain, right? 1 plus this negative sign comes with here, delta g over g infinity, okay? Right? And this is a nice value to have because if we know what our g infinity is, we know what our a is, we can actually calculate what this delta g over g infinity is, right? So the thing we care about, right, is actually this g infinity divided by a, okay? So for example, if you have a amplifier where the gain is 10, let's just say the gain of the idealized amplifier is equal to 10, right? And let's say I have an op amp where the open loop gain is 10 to the 5, right? The ratio between these two guys, right, which is calculated on this side, right, g infinity over a, let's just take the absolute value of it, right, it's about 10 to the minus 4, okay? That means the fractional difference in the gain is 1 in 10,000, okay? So if your output is 10 volts, that means the error on the voltage of your gain is a millivolt, which is pretty good, okay? So that's kind of an interesting thing to note, okay? So yeah, so that's the definition down there. And then the book gave the same example where the fractional difference, right, is this negative 0.001%, which is 10 to the negative 4. Okay, so yeah, and then another example I gave. So instead of giving a gain of 100 when you have a 100x gain amplifier, you're going to get 99.99 instead. Okay, that may not be a true statement. Yeah, so actually that'll go down because knock out one of these nines, because when you put 100 here, right, then you actually it's actually 0.01%. So sorry about that. I think ahead. Okay, so that's sort of neat. So the important point here is that when you're amplifying when you're building an amplifier, you want to keep the amplification kind of moderate. The bigger your amplifier, the bigger your gain is, the bigger the bigger of the uncertainty on the gain will be, okay? Because it's going to be proportional to that, okay? Because your A is basically set by your amplifier, is kind of constant, right? But the G infinity, which is the idealized gain, right, you can tweak that, right? So if you want, so that's why a lot of amplifier tends to stay around like 10x, and then you're going to see like people building series of amplifiers like 10x 10x 10x. Why didn't you just build 1,000, right? Because of this situation where you don't want the amplification to be too large, and we're going to see how this also affects in real life where there's propagation time, which causes these things called slew rates and gain bandwidth. Okay, so let's do a couple more calculations, which is kind of interesting. So this is in the insensitivity of the gain variation. So what we're going to do is keep going back to this closed loop gain equation where we have this idealized gain, right? The gain that you actually get is this idealized gain, 1 plus the idealized gain divided by the open loop gain, right? Because if this number is very, very large, right, the idealized gain basically becomes the gain you actually see in real life. Okay. the way we analyze this time is actually taking a derivative, because what we want to do is figure out how this real gain that we get changes, right, with the open loop gain. Okay, I'm saying a lot of gain, but they are different from each other. Okay, if you take a little derivative and apply your chain rule, what you end up with is g infinity over 1 plus g infinity over a squared, because of this the fraction here that's -1, and so you're decreasing that power by 1, so you get to -2, and then you have to multiply by the derivative of what's inside here, which is actually minus g infinity over a squared. Okay, so with that, right, this time the book actually lay out the algebra pretty well. You factor out this g over a squared, okay, you end up with g infinity over 1 plus g infinity over a, which is exactly what we had before, right? This is exactly what gain is. Okay, am I doing that right? Yeah, exactly what gain is. Okay, so from that point on, what you can do, right, is you multiply the a through this once, and you end up with just g over a plus multiplied by 1 over 1 plus a to the infinity, which is the idealized gain. Okay, so what we're going to do, right, we're not going to deal with just this. Okay, when you multiply both sides of this equation by the variation in a, meaning you don't know how big this open loop amplification is. It could be 25,000, it could be 26,000. So the variation in that is 1,000. Okay, so that's what this delta A represents. Okay, when we do this, right, you basically cancel out one of the delta A's, so partial A, right, and then you end up with the how the gain, right, varies, right, due to the variation in A. Okay, and we're actually also, once again, this is the fractional, right, change in gain, right? Once again, this is same as before up here, right? We're calculating the fractional change in gain. Okay, this is the, once again, right, fractional change in gain, right, due to this variation in the open loop gain 8. Okay, okay. So you can calculate this, and then you end up with is that you have delta A over A, which is the fractional change in the open loop gain, and you have this factor in front, 1 over 1 plus a g infinity. Okay, okay. So the main thing we're trying to get out of this is that, okay, so how does your gain change if, right, the beta function, remember going all the way back to transistor, the beta function in those transistors sets your open loop gain, right? So remember, this not reliable, it could go by a factor 2, go down by a factor 1/2, right? If that's the case, right, if your A is going up and down by a large amount, what happens? Okay, so what this equation is telling us, let's erase this so we can discuss it, is that, right, the variation in gain is proportional, right, to a 1 over 1 plus a over g infinity. Okay, so if we put in some number where g infinity is once again 10, right, our open loop gain idealized version of it, right, is 10 to the, what did the book use before? 10 to the 5, right? A over g infinity, oops, right? This number is 10 to the 4, okay? 1 over 10, well, 1 plus 10 to the 4 is basically 10 to the 4, right? 1 over 10 to the 4. So once again, right, this is approximately, let's do that, right? 10 to the minus 4, okay? So if the open loop gain, meaning the transistor's beta function gain, right, changes by a factor of 1,000, well, let's not do it, changes by a factor of 2, right, the actual gain output that you get changes by a factor of 2 times 10 to the minus 4. So it's still very small. So that's sort of the goal of this section, to prove to you that by using negative feedback in an operation amplifier, you actually really remove this dependency on the open loop gain, which is dependent on the beta function of these transistors you're using. Okay. All right. So the next section, how much time did I record so far? Okay, only 11 minutes. Okay. Okay. So the other thing we're going to talk about is input and output impedance, because this is one of the things that makes op amps really useful. You don't have to worry too much about input and output impedance into the op amp. And the idea is that, right, you can connect something to it and you don't have to worry about it draining too much current and therefore changing what your input is. Okay. Going back all the way back to all these Thevenin's equivalent that we talked about in the first week. All right, so once again, we're going to start with the closed loop gain. We're going to analyze this circuit, right? This the non-inverting amplifier. But what we're going to do is we're going to model the internal, so the thing that's around this dashed line, it's actually inside the operation amplifier. And we're going to model it, even though there isn't like actually a resistor like that inside the operation amplifier. There's a bunch of transistors and capacitors and some resistors, of course, connecting them together. It's more complicated than just RI. But we're going to model it as, well, the input impedance of this op amp directly, right, is going to be, right, how much current goes from the input, the non-inverting input, to the inverting input. Okay, you're going to see how this changes. Okay, so we can determine the current between these two inputs because, well, V plus is just V in. V in minus, right, for this non-inverting amplifier is once again this eta times V out. Remember that eta is just R1 over R2 plus R1, right? It's just the voltage divider equation. Okay. Then we can use that to calculate the current because, right, the current here is basically whatever V in plus is, right, divided by minus V in minus, right, and then divided by that resistance, then you get the current. So let's see how much current goes through here. Okay, in this case, right, V in plus is just V in, V in minus is eta V out. Okay, plug that in. Okay. Once again, what we're going to do is we're going to do a little bit of algebra to finagle things, okay, where we're going to put in, right, what we derived before, that this becomes basically 1 minus eta times the open loop gain divided by 1 plus eta times the open loop gain, okay, and this V out is still here because you just factor that out. Because basically this is replacing what this is. Okay. All right. So this simplifies quite a bit. It's just V in over 1 plus eta plus times A over Ri. Okay. So everything kind of stays. Okay. So what we can do is that we're going to compare this, right, to, right, when we're talking about input and output impedance, right, we care about, well, whatever the V in is, right, equals to whatever the current we get into that times the input impedance. Okay, in this case, it's just going to be R I, right? Okay, so we solve this equation for I. We get V in over Ri, right? Comparing these equations here. Oops. Sorry. Comparing this equation here, I should not have done that equivalence because it's not Ri. Comparing these equations here, right, whatever that is, right, the input impedance is actually 1 plus eta times A times Ri. Okay, so that's kind of nice. Okay, so if we replace eta times A right, with A over G infinity, right, because eta, right, is actually the eta minus 1, right, is actually G infinity, right? Okay, so you can do that replacement. And what happens is that the thing you get out of this equation is that, right, whatever that internal resistance is, right, Ri, that's very important, right? The input impedance, so A is a large number, G infinity is a moderate number, right? So a lot of times A will be 10 to the 5, G will be 10 or 100, right? So therefore, whatever the input impedance of these operation amplifier is, right, amplify this Rin, which is an internal resistor inside the operation amplifier, right, by this ratio of A over G infinity. Okay, so once again, if your the A is going to be very large. If your G infinity, meaning your idealized gain that you're designing your circuit with, right, is not too large, then you're going to get a huge boost in input impedance. And that's what we want on our devices. Therefore, it's not affecting whatever you're attaching it to. Similarly, you can do an output impedance analysis, right? Instead of a input impedance between these two inputs, right? What if we just model this op-amp with a little resistor that's on the output? Okay, remember, this is not a real resistor. This is once again a model resistor that you're adding on to the output of your operation amplifier so that we can quantify how big of a deal this, how does it affect the output impedance. Okay, all right, so this output impedance shouldn't depend on what Vn is. So what we're going to do is we're just going to pick Vn equal to 0. Since V minus is eta times V, okay, times V. We're also going to change the language a little bit because V out is actually the output of the operational amplifier inside. And then V here is, unfortunately, we can't say V out, right? So we're just going to call that V. Okay, so this is the real output that you actually see on the outside. Okay, so what happened is that V out here is going to change by negative eta times the open loop gain, right, times whatever V has to be. Okay, so the current going through this output model resistor, okay, it's just whatever the V is minus V out, because, right, that's what's actually driving the current, right? Okay, because V is going to be bigger than whatever V out is. Okay, and then you get a current that's going into the output. Okay, and then to get the output impedance, right, you divide by RO, and therefore, right, you can see that this is actually your output impedance here already. Okay, so, and since eta is once again 1 over G ideal, maybe we could just call it G ideal. Okay, what happens is that whatever this RO is, right, it's going to get reduced. The output impedance will get reduced from that Ri, right? Once again, this is a large number, right? A over G infinity. Okay, this is a large number, so RO is going to get reduced by a large factor, right? The example we keep giving is that A over G infinity is 10 to the 4, right? So whatever RO is, if RO is 10K, it knocks it down by 10 to the 4, therefore it just gets to 1 ohm. So that's very useful. So you have an output impedance that's almost 0. Okay, because you're using an operational amplifier. Okay, so let's wrap this up. Let's talk about bandwidth. This may be a little bit longer than the other one. Sorry about that. So there are also other non-ideal aspects of the op-amp. We already talked about this, closed loop gain versus the open loop gain, and this G infinity stuff. Okay. There's also a frequency dependence on this open loop gain. Okay, because the faster and faster you go up and down, what happens is that the transistor literally just cannot keep up with the speed of your signal. Okay, and you can model this once again as some sort of low pass filter where A is a function of omega, the angular frequency, right? And this is the, the A naught, meaning the open loop gain at 0, okay? And then a low pass filter has this factor of 1 plus omega over omega 3 dB, okay? And in this case, for operation amplifier, this omega 3 negative 3 dB is going to be a very large number, but at very high frequency, right? Basically, the open loop gain goes down as 1 over omega. And you can see this, okay, if we drive this at increasing frequency. So, there's no scale here, right? But the idea is that as you increase the frequency, okay, what happened is that, let's look at this one up here, which is A omega, exactly what this is, okay? Well, exactly what this is, okay, right? The gain seems okay, but then after your F3 dB point, which is going to be around here, right, it starts to go down by basically linearly, okay? So what happened is that if you have a amplifier that has a large design gain, right, as you increase the frequency, you're going to hit this limitation of your open loop gain sooner, where if you keep your gain at a smaller level, your design gain, what happens is that then you'll hit this later, okay? And the way that the manufacturer quantified this, and this is called, the book calls it gain bandwidth product, but when you look it up in the literature, you're going to see that this has unity gain bandwidth. It's exactly the same number, okay? And the idea is that what you're doing is you're taking the gain and you're multiplying by how much from 0 up to what frequency you get to the F3 dB point, okay? So for the 411s that we're using, this is going to be 4.5 megahertz, okay? So if your gain is 1, right, and you run a signal that's 4.5 megahertz, instead of getting a gain of 1, you're only going to get a gain of 0.707, okay? Okay, so if G is 1, let's just give some example, right? Then that means, and then F is 4.5 megahertz. Right? This design gain, the gain you actually get in real life is 0.707 because you're basically at that 3 dB point. This gets worse, right? Because if your gain is, you're trying to do a gain of 10, or let's just make a bigger one, right? When your frequency gets to, what's 100 times less than this? 45 kilohertz, right? At this point, you are already getting a real gain of 0.707 already. So you're limiting yourself in frequency, right? If you have bigger gain, so you have to balance the two when you're designing your amplifier, okay? Another quantity is called the slew rate. This is related to the unity gain product, bandwidth product. There's some slight difference, especially when you're doing applications. Okay, this basically quantifies how fast the output can change in volts per microsecond. Okay, if you look up the LF411, it's going to be half a volt per microsecond. Okay, that may not seem like a lot, but if you convert the microsecond to regular seconds, right, it's actually 500,000 volts per second. That's how fast it can switch. Of course, it never reaches 500,000 volts, of course, because you're capped at your power supply. But that means it can switch voltages up and down very quickly. Okay. The reason that volts per microsecond scale is nice because that's basically how fast your signal is. If you are at 1 megahertz, 1 megahertz is has a period of 1 microseconds, right? That means if your signal is 1 megahertz, right, your the LF411 can change half a volt in that period. Okay, so in real life application, if you're using the LF411, you really don't want to use it above 100 kilohertz because you're just switching the voltage change is just going to be too slow. Okay, last thing, I hope, yeah. It's just some stability compensation. Yeah, so one thing you could do in order to deal with these high frequency signal is by adding a compensation capacitor to just slow down the amplification. So you're just kind of stretching it out. Okay, you're doing kind of an integrator. Okay, so that's all for this. Sorry, it's a little long, so I will add that together. Thanks.